So we now saw two types of current, the conduction current and the displacement current. Now let us try to take this a bit further. Conduction current and displacement current. One we named IC, another we named ID, and we saw that this is due to the changing electric field. This is due to the changing electric field, and this is the normal conduction current. This is the normal conduction current. Okay. And this is obviously called displacement current. This is called displacement current. Okay. Now, field of flux, fine. Because if you field or flux, if there is no field, there will be no flux, right? So the field has to change somehow. Fine. Now, since their impact is the same, they have the same impact. In what sense? In what sense? That since we know that an electric current produces a magnetic field, so in the same way, this displacement current should also be producing a magnetic field. Okay. So ID should be creating a magnetic field in the same way as IC. In the same way as IC. Okay. And it is not a hypothetical construct. It's not that it should be and it does not. It should be producing and it does produce. So we can actually calculate the field. Say if I ask you to calculate field at point C due to a charging, due to a charging capacitor. Okay. It is quite possible to both compute and measure this field. It is not a hypothesis. Fine. So at point C, a magnetic field should and does exist. It should exist and it does exist. Okay. It can be both calculated and measured. It can be both calculated and measured. Okay. Fine. And this magnetic field is due to the displacement current. This magnetic field is due to the displacement current. It may strike you that maybe it is the impact of this which is creating a field here. Correct. This thing can come to mind, but if it was a vast empty space, okay, if say I had put this 2 kilometers apart, say, and there was no outside interference, then too that magnetic field can be measured, and if you take into account all the fringing and all, still that value will come out to be what you computed or very near to what you computed. Okay. So what we want to understand is that this is no hypothesis, and it has been experimentally verified that there is a magnetic field, and if there is a magnetic field, there has to be a current which is producing that. That much we know. Okay. Now we know that this is equal to how much? Epsilon naught d phi e upon dt. Okay. This d phi e upon dt, so it'll survive only as long as this has a value. So this comes from there. So that's why it has to be changing, because phi e is nothing but E dot A, right? Phi e is nothing but E dot A. But you will be considering, so for example, in this case, to calculate, say, the field here, you will have the area of the capacitor as the thing where E is concentrated, no? That will give you the full current. Obviously, if you change this area, maybe you say, no, I want to find out current only here, then obviously accordingly the area will shrink and the current will be lower. Okay. If you take a smaller area, the change will also become that small, no? And hence the current will go down. That will soon do to solve a question. Fine. So do we understand this? Now, if you remember, so this produces a magnetic field. What is EMI? What did Faraday say? What does Faraday's law say? What is the whole impact of Faraday's law? Faraday's law, otherwise you'll find yourself recalling that it is this. Correct. So there is a potential that is produced. There is a potential difference that comes into play the moment the flux across something changes. Correct. So the EMF that is produced is this. But I want to take you further, and we had discussed that while we were discussing the EMI, that in one of the cases where he did not move anything, what he did, one of the coils he just switched on, and the other coil he found there was there was there was a there was a there was a potential, right? So what happened there? An EMF was induced when he did not do anything. Say there was a coil here, there was a coil here, and he just switched it on. And say there was another coil here, where he had just put the galvanometer. What did he see? He see that even in this case there was an EMF induced and a resultant induced current due to the fluctuation in this. Now earlier what was happening? There was some movement. Fine. When say this was moving, then we attributed the movement of the electron to what? To the force QVB. Okay. That was the force experienced by the electrons due to the Lorentz force, QV cross B, correct? Now what was the cause of the flow of current here? That is fine. But the very fact that this is moving, the electrons here are moving, it means there is an electric field out there. So it takes you beyond this. It tells you the real impact, the real import of the Faraday's law is, the real thing about the Faraday's law is very significant, and it says that somehow a changing magnetic field is able to produce an electric field. Okay? So the real impact is that a changing magnetic field is capable of producing an electric field. Okay? A changing magnetic field can produce an electric field. That is the most important conclusion of the Faraday's law. Okay? And what is the impact of, so this is my magnetic field producing an electric field. Fine. What is the impact of this? What is the impact of this? That there is a changing electric field which produces a current, which produces a magnetic field. So I can say that Maxwell's law gave me this. Maxwell's law gave me what? That a changing electric field produces a magnetic field. You see, electricity produces magnetism. The counterpart is that magnetism also produces electricity. That was the whole discussion that revolved around in chapter of electromagnetic induction. Correct. So electricity produced magnetism. So the question was, does magnetism also produce electricity? The answer came to be yes. He said a changing magnetic field is capable of producing an electric field. So actually we were waiting for this to happen in a sense.
But we already got that, right?
From where?
Faraday's law.
No, we got this. The reverse we didn't get.
No. We got that in the chapter that we did in magnetism and matter.
Where?
When we were doing that, due to current, there was magnetic field produced. So obviously.
No. This is a different field. This is a different thing altogether. This is, if the field is not changing, if it is steady, then it cannot produce that D.
Okay, only ID, but it will produce a magnetic field if it is steady.
If it is steady, it won't. That's what we'll see. Shortly we'll see that you cannot produce this field, this displacement thing with a steady current. That's a different thing altogether. A steady current will not be able to produce this. Okay. So a changing electric field produces a magnetic field, obviously by first producing a displacement current. Okay, by first producing a displacement current. Fine. So as it happens that nature is symmetrical, so we have seen so many symmetries coming out at us. Fine, and this is one of them.